Hi there! Whether this is new for you or just a review, welcome to the fundamentals of logic. Maths does get very complicated, but here we're going to try and start from the beginning. The topic of logic, though, is not something you learn when you first start maths as a child. It's just too abstract, but it is the very basic ideas that make maths work. So what is logic exactly? Logic is the science of thinking systematically. In other words, thinking like a machine so that the same inputs always give the same outputs. You might think that this sounds cool and important. You might think it sounds horrible and scary. It's kind of both, but that is another topic. Logic was first studied in the West by Aristotle over 2,000 years ago, and in the East at about the same time. Since then, it has become much more organized and well-defined, and mathematicians love making things well-defined. The foundation of logic is statements. Statements, or propositions, are sentences which declare something. A statement can be true when it declares something that exists, or false when it declares something that does not exist, but it cannot be both. Here are some examples of statements. February has 30 days. 4 plus 2 equals 6. George Bush was the US president, and tomorrow is Tuesday. So, depending on when you're watching this, either 2 or 3 of those statements are actually true right now. There are other sentences that are not statements and cannot be either true or false. For example, have you done it? Please hand me a towel. Do you want to dance? And stop the bus! These are useful sentences, either questions or commands, but they cannot be given a truth value. They cannot be either true or false. Let me focus on the idea of a truth value, just the idea of a statement being true or false. This seems obvious, but it's also absolutely important. Truth values are binary. They are always in one of two states, true or false. Computers also use binary. The basic unit of computer language is the bit, or the binary digit. And that is either a 1 or a 0. A bit is the most fundamental unit of information. It is the smallest amount of change where it is possible to communicate anything at all. Up or down, yes or no, in or out, 1 or 0. Truth values are, very simply, the foundation of all meaning. They are the only way that it's possible for anything we say to transfer information. But how do we go from statements and truth values to all the different work that we've done in maths and other subjects as well? We do this by using axioms. Axioms are statements that we just assume to be true. That's it. We just assume. Every system needs some axioms, and sometimes we find new ones. It doesn't sound very scientific though, right? Aren't we just guessing now? Well, yeah. There have to be some guesses, but we try to make our ideas precise and then we test them against other theories and what works in the real world. This is how we work towards making better guesses in the future. Now we're going to construct some more complex statements, or compound statements. In chemistry, a compound is a substance that is made of 2 or more different elements. And in logic, a compound statement is a statement that is made of more than just one simple statement. This usually uses some connecting words, but let's look at some examples to make it clearer. I'll just run through the basic types and then we'll look at them in more detail. We've already talked about simple statements, a sentence that declares something true or false. Then we could also have a negation, which is a simple statement that has a reversed truth value. We will usually use a word like not or some other negative word. Next, we have the conjunction, which is 2 simple statements connected so that both are suggested to be true, maybe using a word like and or but. Next, there is a disjunction. These again are two simple statements, but they're connected so that at least one is suggested to be true, probably using the word or. There are two types of conjunction, but we'll come back to those shortly. A side note, but just because a compound statement suggests one or more statements are true, it doesn't mean they actually are true. We have to decide after that whether they are true or not. Another type of compound statement is the conditional. This says that the truth of one statement depends upon the truth of another statement, such as when we say that if one thing happens, then something else will happen. Finally, there is the biconditional, which makes a two-way conditional between statements, so the if-then relationship will go in both directions. Now we'll go through each of these in more detail, along with how we use them in doing logic. We will start again with the simple statements. Simple statements must be either true or false, and not both. Here are two more examples. Marlon is a rat, and all rats like cheese. When we use logic, it's common to give each sentence a letter so we can use it in a more mathematical way. Let's say that the first sentence here is P and the second is Q. So P stands for the idea that Marlon is a rat, and Q stands for the idea that all rats like cheese. Now that we have two simple statements, we can make a simple argument. When we make an argument with statements, each statement is called a premise, and these lead to the conclusion of the argument. So if we have premises P and Q, like above, then what do you think the conclusion would be? Pause if you want to come up with your own attempt, but I'll tell you that if Marlon is a rat is true, and all rats like cheese is true, then we can conclude from our premises that Marlon likes cheese. We can call this R. This is almost too simple to be a real argument, but you can see the idea of connecting statements with logic to lead to conclusions. We give our statements letters so we can write the whole argument down in symbols. One common symbol to show the conclusion is the double turnstile. You can think of this as standing for the word therefore. Everything on the left is true, therefore everything on the right should also be true. This is called entailment. Let's move on to negations. As we said before, these are simple statements with a reversed truth value. So if P is Marlon is a rat, then not P will be Marlon is not a rat. And if Q is all rats like cheese, then not Q will be all rats don't like cheese. Not Q is actually ambiguous. It has two possible meanings. You could think about how, and I will tell you at the end of this video. The symbol we will use for negations is the not symbol, which is a little square hook symbol. There are other symbols for not and other logic functions too. Here is an argument that works with negations of our simple statements. We can combine not R, Marlon does not like cheese, with Q, all rats like cheese, and we can conclude that not P, Marlon is not a rat. As a quick question for you, is it also okay to combine not P with Q to get not R? Pause if you want to think about that. The answer is no, that would not work. And let's quickly see why. It all comes down to what we know from Q. Q only tells us that rats like cheese. We know Marlon isn't a rat, but there are lots of other things that do like cheese. So we know he isn't a rat, but it doesn't follow that he doesn't like cheese. Maybe Marlon is a human and he just loves cheese. The same thing would happen if we try to reverse the simple version of this argument from earlier. And it should start to show you that we have to be very careful when planning logical arguments. And we've only looked at two types of statements so far. Let's move on now to conjunctions. Here are two examples. Alan is here and Beverly is here. Or Beverly is here and Carl is not here. These compound statements suggest that both parts are true. Conjunctions use an inverted V sign or others as a symbol. Question for you. If A equals Alan is here, B equals Beverly is here, and C equals Carl is here, how would you write these conjunctions in symbolic form? Pause if you want to try it, but we can show them like this. We place the inverted V between our two simple statements. Note that the simple statement C needs to be negated to become not C. Carl is not here. If you said A and C, then that could be okay. There is no rule that says we can't have a simple negation, but logicians may frown at you. Not all conjunctions use and. Take a look at these three different statements. All of them suggest that both A and B are true. Alan is here and Beverly is here. Alan is here but Beverly is here. And Alan is here even though Beverly is here. These may all be conjunctions, but they are not the same sentence. Different connective words suggest that there is some missing information. For example, Alan is here but Beverly is here suggests there may be some kind of problem that happens from both people being here. Alan is here even though Beverly is here suggests that Alan might have a reason not to be in the same place as Beverly. In an argument, missing information like this would be called suppressed premises, something we are not saying, and you should always try and find any suppressed premises in your logic. Now we come to disjunctions. Two examples are here. I will drink water or cola, and either I will run home or I will take a bus home. As mentioned before, disjunctions suggest that at least one of these simple statements is true. The most common word used in disjunctions is or, but we do need to be careful here too. There are actually two types of disjunction. Look at our examples. In the first sentence, I can have water or cola, or I could have both. But in the second sentence, if we're talking about just one trip, then I have to choose one way to get home. I run or I take the bus, but not both. The first type of sentence is called an inclusive or, and it's shown by the letter V. Try it. If F equals I drink water and G equals I drink Coke, how can we write the inclusive disjunction? Once again, pause if you would like to think, but I can show you it would look like this. Again, the symbol for the connector goes between the letters standing for statements. The second kind of disjunction is called the exclusive or. It is shown by a V that is underlined. So if H equals I run home and J equals I take the bus home, what is the exclusive disjunction here? In fact, it will look like this. Let's just stop for a few examples. Try to symbolize these sentences using the statements we've seen so far. Keep it simple. Assume that all disjunctions are inclusive for these examples. Pause if you want time to think, and we'll show them in 3, 2, 1. I hope you can go through and see how each of these examples work. I'll just say a couple of things. First, you can see that many of these sentences are rather silly. Just because we can say something in logical terms, that doesn't mean it's correct or even makes sense in the real world. Second, in the last example, we've used a set of brackets. Don't worry if you didn't, we will look at that in a future lesson. But very roughly, brackets are used in the same kind of way as in other maths topics. Next, we come to the conditional, which makes the truth value of one statement depend on the truth value of another statement. Conditionals are often in the form if A, then B, but there are many other ways they can be written, and some of them can be quite confusing. Be very careful with conditional language. Let's look at some examples of conditionals. Here's one. If you study hard, then you will get a good grade. So this suggests that if it is true that you study hard, then it will also be true that you get a good grade. And we can see something similar in the second example. If you eat a bucket of ice cream, then you will be sick. So we can see that the outcome depends on the condition, but it only claims that if the condition is true, then the outcome should be true as well. It is still possible to be sick if you don't eat a bucket of ice cream after all. And it is also possible to get a good grade if you don't study hard. But don't rely on that. The condition is shown using a one-way arrow that points from left to right, from the condition to the outcome. As we said before, there are conditionals that are not written in a simple if-then form. Here are some examples. See if you can rewrite these conditionals into an if-then form and write them using the symbols above. Pause if you want to think again. Just like the others, the conditional arrow goes between the two letters. The first one, if I am hungry, then I eat something. If K, then L. In the second one, the wording actually reverses the order. The phrase as long as kind of means depends on, so the condition is actually at the end. So it will be, if I get the next train, then I will be early. If N, then M. We should also mention the formal words for the condition and the outcome. The condition is called the antecedent, and the outcome is called the consequent. These words are very formal, but they are still used a lot when you read about logic. Finally, we're going to look at the biconditional. The biconditional is like a two-way conditional where both statements depend on each other. Remember the example on the last slide? If you eat a bucket of ice cream, then you will be sick. Well, imagine if the only way anyone ever got sick was by eating a bucket of ice cream, but every single person who eats a bucket of ice cream always got sick. That would be a biconditional relationship. Let's look at some more sensible examples though. Two angles are congruent if and only if they have the same measure. Two angles are the same size, so we will find them congruent, because congruent means being the same size. If and only if is the way that we say the biconditional in everyday English. And I also forgot to mention that the biconditional is written with a double-headed arrow, like you would expect for a two-way conditional. Another example might be to say that a car is parked if and only if it's not moving. But we have to be careful here and add using its own power, because sometimes parked cars can move around, like in this picture. Again, we can see that these relationships can get messy if we are not very careful with our language. The difference between a conditional and a biconditional can be quite subtle, and you'll get used to deciding when to use if and when to use only if. We'll talk more about that in the future, but we can define the biconditional quite well using the other types of statement we've already seen. A biconditional is the conjunction of two conditionals where the antecedent and the consequent are reversed. Can you write what that means using the symbols we've seen earlier? Don't worry if you can't, and if this language is still very confusing to you for now. Pause if you need time to think though, and just go through the sentence piece by piece. I can show you now that it is this. We have two conditionals with reversed statements. If we have A then B, and we have B then A, between them we put the conjunction, so we're essentially saying that both conditionals are true together. If A then B and if B then A are both true. Now, see if the definition makes a bit more sense. The biconditional is the conjunction of two conditionals where the antecedent and the consequent are reversed. If you have followed the previous slides in this lesson, you've now looked at all of the basic functions of logic. There is plenty more to come, of course, but here we can see a summary of the logical symbols we've looked at so far. Have a quick review for yourself. Go back to any slides you think you aren't clear on. Don't worry if you aren't sure about all of them yet. It takes practice to get used to them. You might also see that there is more than one type of symbol for many of these functions. Different systems have been used for logic, so you have to watch out and be ready to look up alternate symbols. But I think I've chosen the most common version of each. Before we finish, I want to tell you a secret. Logic likes to pretend it's very clear and always accurate, but there are some really weird parts of logic, and I think it's important to show that although logic is incredibly useful, it's not a perfect system, and we still have things to learn. That said, the rest of this video might make your brain hurt a little bit. Don't worry, these things are much more complicated for the future, but I want to introduce them so you know that they're coming. There are some statements that cannot be given a truth value. These are called paradoxes. For example, the statement, "This sentence is a lie," is a paradox. I am stating that "this sentence is a lie" is true. But if I'm telling the truth, then I'm actually not lying to you, and therefore the statement is false. However, if I am lying to you when I say that I'm lying to you, then the statement is true, so I'm not lying to you. We cannot give this statement a truth value, even though it seems to be declaring something clearly like statements should. Paradoxes can be quite confusing, unsurprisingly, so we're not going to go into them any further, but they are an interesting part of logic, and trying to untangle these strange effects is how we create new ways of thinking. There are also other types of logic. I said statements must be either true or false, and in regular logic, that's right. This is often called Boolean logic after the mathematician George Boole. But there is another form of logic with degrees of truth. For example, a statement might be 30% true and 70% false. This is called fuzzy logic, and it was first investigated in the 1960s. Fuzzy logic is an important part of modern computing and AI systems. It tries to use the ideas of logic on situations which are too complex to easily break down into Boolean logic. We're going to stop talking about fuzzy logic now and stick to more formal logic in these videos. We said at the start that logic is the foundation of maths, but we haven't really seen any maths yet, have we? For now, just remember that logic is based on axioms, and maths has to use some axioms to start from, which we can look about in the future. But think about this. Using the symbols we have learned so far, we can make the argument that if I have one thing and I have another thing, then I have two things. 1 plus 1 is 2. To be clear, this is absolutely not how mathematicians prove that 1 plus 1 is 2. That can take hundreds of pages, and no, I'm not kidding. Finally, I need to say what logic is not. Logic is not morality. Some people forget this sometimes, but in logic we focus on what we can say is true or false, which is not the same as saying what is right or wrong. The two do cross over sometimes, and when they do, people get pretty upset about it. But enough of that for now. No one can go from what is true to what should happen. This is sometimes called the ought-is problem, and if you don't believe me, try it. See if you can logically derive I should from it is true that, with no suppressed premises. If you can, then your Fields Medal in Mathematics is waiting for you. Okay. That was a lot in a short time. If you followed all of it, then well done. But you probably don't have it all perfectly if it was your first time through. If you didn't follow it, don't worry. This is the very start of a big subject, and you can break down each subject of this quick introduction to find where you need to listen again or read further. And you should also do some practice problems to make this feel more natural to you. If you are still confused, you can watch again or try someone else's explanation and examples. If you keep at it, then you can become comfortable with logic. And although I just said it was not perfect, it is still very important. Everyone needs a way to be sure what is true and false sometimes. Oh, and last of all, let me go back to not Q. All rats don't like cheese. Remember I said it had two meanings? The first is that all rats, every single rat in the universe, don't like cheese. The second possible meaning is something more like there's at least one rat which doesn't like cheese. It's not true that all of them do like it. In normal English, we would have to find a way to confirm between these two options, but logic has a way of making it clear. But that is for another video. Hi, hope you found that interesting. Like, comment, subscribe, etc. If you prefer shorter videos, you can find this cut up on our other channel just up there. But whatever you do, please keep learning something, because no matter who you are or how old you are, every day really is a school day. Bye for now.